everybody, I'm going to talk about epoxide ring opening reactions in acidic conditions in this video. So if you haven't checked out the last video on strong nucleophiles, definitely check that out. This one is going to be the opposite end of that, where the strong nucleophiles is more kind of basic type conditions. If we're in acidic conditions where we've added some sort of strong acid, we're going to be looking at slightly different reactions, okay? So, but we're still going to go by a very, very similar mechanism here. So let's go ahead and take a look at the same substrate that we had in the other video. Okay, let's look at this epoxide. So now we're going to react that with methanol and sulfuric acid. Okay, so as soon as you say the word sulfuric acid to yourself, or any kind of word that ends in acid, the first thing that you do is probably going to be a protonation. Okay, so we're going to see an acid-base reaction happening between our epoxide and our sulfuric acid. So keep in mind here that the methanol and the sulfuric acid can absolutely have an acid-base reaction as well, where you have some protonated methanol around, and you're definitely going to have some protonated methanol around in this. Not all of it's going to get protonated though, because you have a lot more methanol in your reaction than you will have sulfuric acid in your reaction. They're not in a 1-to-1 ratio here. But for these purposes, we're mostly just looking at the protonation of the epoxide, but just so that you know, the methanol does get protonated as well. Okay, so we're going to use our oxygen of the epoxide. It's going to grab a proton from sulfuric acid, and that's going to give us our conjugate base. And our conjugate acid. Okay, so now that is positively charged. So if I'm looking at these two structures and comparing them, so if I'm looking at this one and this one, the top starting material that's neutral is a weaker electrophile than this one is. Okay, so because I have that positive charge, it's pulling electron density very, very strongly towards the oxygen, and then making those two carbons of the epoxide more delta plus than before. Okay, so this is a strong electrophile, and we're going to say this is a weaker electrophile. You know, it's not like super weak, but when you're comparing this to this one's definitely stronger. Okay, so if we're looking at this, one thing that we want to consider here is, I know that both of these are delta plus, but are they both evenly the same amount of delta plus? Okay, so we want to look at that. Okay, so if we're thinking about, I'm going to try to draw this a little bit larger here. So if we're thinking about these two carbons, right? If I've got these two, one of them is a lot more substituted than the other one, right? This one is more substituted. If we're thinking about the things that stabilize a carbocation, for instance, that carbocation needs to have substitution around it, essentially to donate electron density into that kind of electron poor location. So the same things are going to stabilize the carbons in an epoxide, because this oxygen is so desperate for electrons, it's going to pull from those carbon oxygen bonds. And the way that it's going to pull is it's going to kind of lean away from the carbon that can handle that positive charge the best. Okay, so we're going to kind of pull that way. So it's going to lean away from that more substituted side. that can better stabilize the delta plus. Okay, so if we're looking at this delta plus is much, much bigger than that delta plus. Okay, so we've got one that's got much more positive charge associated with it, much more electron poor, versus this side is going to get more electron density because the oxygen is kind of not pulling from that side quite as hard. Okay, so when I'm looking at something like methanol as my nucleophile, right? Methanol, remember, is a very weak nucleophile. So it needs a really strong electrophile. Okay, so I need to be attacking the strongest, most electron poor location. So we're going to go and attack at that carbon with the delta plus, the biggest delta plus, and then we're going to open up that epoxide. So our arrows here are identical to the ones that we saw in the strong nucleophile video, but the location that we are attacking is opposite. Okay, so we're going to open up our epoxide. So that OH is still on a wedge over here. And we need to think carefully about what's going on this side. So if I'm doing these arrows, that's a lot more SN2 type arrows than SN1. The regiochemistry, or the carbon that we're actually attacking, is very much SN1 in terms of we're going for the most substituted side. But if we're looking at the arrows, that's a total SN2 type reaction arrow. So we're still going to be getting inversion of the stereochemistry on that carbon that we attacked. Okay, so, oops, what am I doing? Not that. So if my epoxide is facing forwards, that methanol is going to be coming from behind. And we're going to end up here. Okay, so at this point, I just need to do a final deprotonation to get to my final product. I can use methanol as my base here. So I get to this product. Okay, so our stereochemistry still get that anti-relationship between our nucleophile and the oxygen from the epoxide. But now we've got the substitution occurring on the more substituted side. Okay, so in acidic conditions, the nucleophile attacks the more hindered side. Okay, we're still getting inversion of stereochemistry. Like with SN2. Okay, so the more hindered side, think about that like SN1, how SN1 substrates prefer to have the carbocation in a more substituted location. That's what we're looking at here. Okay, that more hindered part is very SN1-like, but the stereochemistry we're seeing is still very SN2-like. Okay, so one thing that I did not talk about, though, that we need to address is why I didn't do anything with that. Okay, so why am I using sulfuric acid and not something else? Okay, so sulfuric acid is a very specific choice here and it has to do with the features of this conjugate base. So we've seen a lot of instances now where we have a conjugate base created that can actually be a nucleophile, okay? Because this negative charge is so incredibly delocalized and so incredibly stabilized, I'm just going to draw these resonance structures out. Right, we have it delocalized over 3 oxygen atoms. Okay, that's going to be a very, very stable negative charge. It's going to be very stable and a very bad nucleophile. Okay, whenever we've got the conjugate base of sulfuric acid, it's totally fine just staying that way. Okay, it can't really collect enough electron density in a single location and have it be localized enough to actually act as a nucleophile. So this is not a nucleophile. Okay, so if we're looking at this though, we do know of some acids that do give us good nucleophiles from their conjugate base. So let's look at another example here. So let's say we're going to use HBr. Okay, and in this case, HBr is the only thing I'm adding to this reaction. It's pretty sparse, but that's what we're using here. Okay, so HBr, I've got hydrobromic acid. First step is going to be to protonate. So I'm going to go ahead and protonate. Protonate the oxygen of my epoxide. And then I'm going to end up here. Okay, and I've got Br minus, okay, as my conjugate base. So Br minus is actually a pretty decent nucleophile. So this is a good nucleophile, bad base. But we can do a substitution with it. So we can go ahead and use one of those lone pairs. And again, we're going for the more substituted side because we have acidic conditions. So this is going to be a really good electrophile. We're going to pop open that epoxide. And again, we're coming at this with inversion of stereochemistry. So bromine's going to come from the back. That's going to push that methyl group to the front. And then my epoxide is going to open so that my OH stays on that wedge. Okay, so I'm going to end up with that product. And that for that one, that's all you need to do. There's really just the protonation and the nucleophilic attack step. So we can also do this with HCl and HI as well. Okay, so we can use those kind of HCl, HBr, HI as proton sources and nucleophiles. Okay, all of those things together. Whereas the sulfuric acid, since the sulfuric acid is not a nucleophile, it's only a proton source. So we have to go and add in a separate nucleophile for that reaction. Alrighty, so as always, let me know if you have any questions, and I will see y'all later.